recording. Okay. How's everyone doing today?
Doing well, you?
Pretty good. Okay. So today we're going to be doing lab 6. And in this lab, we are going to be doing a 3D truss. So we're going to consider the 3D determinate truss shown in figure 1. The overall height of the truss is given as 20 feet. The base dimensions are 5 feet in the Y direction, 8 feet in the X direction. And we're going to consider the self-weight of the structure to be 0. So we scroll down. We've got a picture of the truss we're going to be doing here. If you recall, you might have seen this one in the textbook. So we're doing one of those problems. I added some loads on there. But we're going to be analyzing this one today. I think you guys had a little bit of experience doing 3D trusses in class already. So I'm sure we can all appreciate that the computer can go and do all these for us now. Yeah, so it's doable by hand. And for a long time, people used to try and make trusses or make their structures trusses because they can be determinate like this. And they're more feasible to analyze than frame structures are by hand. But now that we have computers and more computational power that way, we're not necessarily limited to the easier analysis methods. So I mean, technically you can analyze any of these structures by hand. It just can take a while for highly indeterminate structures. So trusses have been nice in the past, especially 3D trusses, to alleviate some of those indeterminacies. Okay, so what we're going to do is we're going to launch SAP, and we're going to model the truss here, load it, and do the deliverables. Units are going to be kips and feet. We're going to be using steel. The cross-sectional properties for each of the bars in the truss is going to be an HSS 3x3 by 1/4. The loads are shown on the figure there, and we're going to have one load combination this week right here. And to help make modeling the truss easier, we have the coordinates of each of the nodes on the truss there given in the table here. So let me launch SAP. Any questions on the assignment this week? Straightforward enough? Okay, that's good.
Not really a question, this is a comment.
Uh-huh.
I accidentally submitted both the assignments 4 and 5 in the wrong spot. So like they're flip-flopped in mine.
Okay, you can resubmit the right one in the correct spot.
Okay.
Yeah, I'm pretty sure, unless I didn't do it right, you should be able to do that.
No, I was just on that. Not all.
Oh yeah, no worries. Okay, so when we get SAP up, we'll make ourselves a new model. All right. Anyone need another couple seconds to get SAP going? Okay, cool. So units we're going to be using here are kips and feet. So make sure we select kips and feet from our drop-down here. Now, in our templates down here, you may be tempted to say, hey, look, there's a 3D truss template. Let's use that one. But we're not going to be using that one this week because there are all sorts of geometries you can make 3D trusses out of. And this problem does not happen to be one of the ones that the template's set up for. I certainly encourage you to go and explore all the templates and mess around with the program as much as you want. Really good learning that way, seeing what it can do. But 3D Truss template's not going to help us this week. What we're going to want to do is we're going to want to use a grid-only template. So we're going to click on grid-only. And what we're going to want to do today is we're going to set up a singular kind of snap to point at the origin. So the way we can do that is we can go and set the number of grid lines in each of our axes just to 1. So if we intersect 3 perpendicular lines, that'll just give us a single point. And we're going to go and insert our nodes based off of the coordinates in the table in reference to that point at our origin there. So it doesn't matter what the grid spacing you have here is. I'll just set that all to 1. But you need 1s in the top 3 and 0s in the bottom 3. Make sense? And we do this to just get ourselves that one single snap point at the origin. Because if we just clicked on blank, then we wouldn't have anything to snap to at the origin, and it'd be harder to go and insert the nodes where we need them to be. Okay, so we've got 1s here, 0s here. When we're happy with that, we press OK. Let's see here. I don't need that view. We're going to be working in 3D today. So I've got my 3D view here. We've got our axes, X, Y, and Z. And we see we have our one point we can snap to, the grid point there at the origin. Everyone getting that? Okay. So now what we're going to do is we are going to use there we go. We are going to use the coordinates here to go and insert all of these nodes in our model. So up to this point, what we've been doing is we've been drawing in our elements, right? And when we do that, that'll automatically go in and draw in nodes on either side of the elements. And that's kind of happening in the background. However, when we have a structure like this, it's going to be kind of hard to go and draw all these elements all over the place unless we have some nodes to snap to. And we can do that by going and creating a big old complicated grid that would have a snap point at each of these nodes right here. But when we have kind of large structures like this, that can get kind of messy, especially when stuff isn't spaced evenly. So I'll show you how we can insert nodes in arbitrary positions in 3D space to model this a lot more cleanly. So we can snap to our origin here. What we're going to do is we are going to use our draw special joint tool here. This is right above the draw frame / cable tool we usually use. So we're going to click on the draw special joint there. And we get this menu right here. And we have offsets in our X, Y, and Z direction. And what we're going to do is put in our X, Y, and Z coordinates in these offsets. Then we're going to click on our origin. So it will offset our point to its right coordinates in space. So this is a pretty neat trick to go and put a node at some arbitrary coordinates in your model here. So we're going to put 3 here. We're going to put minus 2.5 here. And then we're going to put 0 and Z there. And when we're happy with that, 3 minus 2.5 and 0, we're going to click on our grid point, and it's going to insert the node. Now, it might be out of frame when we click on that. So what we can do is we can go to click Restore Full View. It's the magnifying glass with the dot in it on the top. And that will give us a view of the model kind of centered on the middle of the model there. Make sense? And we're just going to repeat this for the rest of these points here. So for point B here, we're going to put in 3. We're going to put in 2.5. And then Z is still going to be 0. So we're going to click on our grid point again when we're happy with our offsets. And we see we now have our second point in our model there. We're going to do the same thing again for C. So instead of 3, we have -5. Y is still 2.5, and Z is still 0. So when we're happy with those, we can click on our grid point again. It's going to pop off somewhere over here. So let's go and click on our restore full view again, so we can see all 3 of our points in space. So that's the first 3, and we're going to do that same thing for the next 4. Any questions on this so far, or anyone getting something different? Yeah.
So when you set your new offset points, do you click on the origin of the box, or do you click on the point you just created?
You will click on the origin right here.
Okay, just clicking the origin.
Yeah, exactly. Because if we went and clicked on one of these other ones, it would be these coordinates offset from that point, which would not be where we want it necessarily.
Thank you.
You could do it that way if you went and defined your coordinates in terms of that point. Okay, so for point D here, we'll have 1.5 minus 1.25 and 10. So let's click on that. We will have 1.5, positive 1.25, and 10. So click on that. And then we'll have minus 2.5, 1.25, and 10. So then we'll click on that. And then for our last one, we're going to have 0, 0, and 20. And then we'll click on our origin. And then if I go and restore full view, we can see we have all 7 of our points there. Okay. Any questions on inserting nodes like that? Okay. So now we're done with this tool. Let's press escape so we can exit out of the tool there. So we're not going to accidentally put in any extra nodes. Now what I want to do is so that I can draw in everything between all the right nodes, because you see these all have labels, but we don't have any labels over here. We're going to go and rotate our model so that our coordinate system here goes and lines up with this coordinate system over here in the picture we have. So we can go and do our 3D rotate, which we can do with Shift and holding down your middle mouse button to go and rotate your model around. Or you can go and use the rotate 3D view button, which is a little kind of moment looking arrow there next to the sunglasses. So we're going to rotate our model around until we can get our coordinate system lined up pretty similarly to the axes over here. So we have our x direction coming down this way, our y axis coming this way, and our z axis going up. Does it make sense what I was doing there? Okay. Everyone up to where we're at here? Okay. So the next thing we want to do is we want to get 2 things ready before we go and draw in all of our elements here. So the first is we want to import the cross-sectional property that we want for these shapes right here. And if you remember, that's going to be an HSS 3x3 by a quarter. So we'll go to define, then section properties, and then frame sections. So this is where we can go to import properties for our shapes here. And we'll click on import new property. And if you remember, an HSS is one of these square tubes right here. So we'll click on that. We'll click on the AISC15 database. We'll open that. Then we will look for the HSS 3 by 3 by 1/4. Oh, there it is right there. HSS 3 by 3 by 0.250. We'll press OK on that, then OK on that, and we will have that imported here. Questions? Are you guys okay? Okay, so we will press OK then. And then what we want to do is we're going to go and select the draw frame / cable here. And we have a couple options here. Now we see that it's going to be a straight frame. That's okay. The section is the one we just imported. So that's okay. And then we have moment releases here. Now, do you remember back from our first lab, what was one of the things we needed to consider when we were modeling a truss? What's the big difference between a truss and just like a regular frame? At the joints, exactly. So all of your joints act like hinges. So we don't have any moment transfer across any of our nodes. So what we can do here is instead of continuous, we can go and tell our moment releases to be pinned. Yeah. We go and click on the draw frames / cables item right here, and that should pop up. So we'll switch the third option here from continuous to pinned, and this will go and release those moments as we draw them here, instead of needing to go in and release them at the end here. And then the rest of this is okay. So when we're happy with that, let's go in and draw in our members. So we can go and draw in our members from A to B and B to C and C back to A. We can go and draw in our members from D to E to F and then back to D. We'll have the kind of 3 edges of our little pyramid here. And then we're going to have a member for a brace from B to D. We'll have a brace from C to E here. And then we'll have another brace from C to D here. And then finally, we'll have the 3 going to the peak at the top. Okay. Yes.
How did you rotate the model?
So you can rotate your model around using Shift and hold down your scroll wheel.
Okay, there we go.
No. Yeah. Programs are kind of weird sometimes. There's like a couple they're all like pretty similar in how they move around, but some of them pick like different extra keys or something like that.
That's it's command and shift, right?
Yeah. Yeah, so this one's a shift in the middle mouse button to rotate around. Okay, everyone's look like this. Okay, cool. And then one last thing we want to do before we're done with drawing all of our geometry here is we want to add in our boundary conditions. So if we look at our model here, we have these ball and socket connectors at A, B, and C. So that's basically just a pin in 3D. So that allows rotation in any direction, but no translation in any of the directions. I believe the way they drew it here for the textbook is so that it's like technically a determinate truss. If you have like a 3D pin at each of these joints, it's technically like a indeterminate to the third degree because there's 3 extra reactions that you don't have equilibrium equations for. But it's the computer, it doesn't care. So it's way easier than figuring out how to go and model these boundary conditions here. It's doable, just a little out of scope for what I want to teach right now. So we're going to click the 3 points at the base. Then we're going to go to assign. And then we're going to go to joint and then restraints. So same place we always go for our boundary conditions. Assign joint restraints. We're going to click on our 3D pin or our pin right here. We see it's going to stop translation in all 3 directions. It doesn't care about rotation. So then we can press OK, and we have our 3 pins. Okay, everyone good with that? Okay, so that's all of the geometry. Now for the loads. First things first, we have 2 types of loads. We've got dead loads and live loads, and we'll have a load combination. So let's set up our loads, and then let's set up our load combination. So we'll go to define, load patterns. And we see here we have our dead load. Now, in the model here, or in the brief here, it asked us to set the self-weight of the structure to be 0. So while we're here, we'll set our dead load to 0, and we'll say modify load pattern. So it's updated to 0 down here. And then let's add ourselves a live load. And that will still have a self-weight multiplier of 0. So we'll say add new load pattern, and we have our dead load and our live load in our table down here. So same as we've been doing. Okay, any questions on that? Okay. So those are our loads. Now let's add our load combination. We want 1.2 dead load plus 1.6 live load. That's a very common gravity load combination here. So let's add that. So we'll go to define load combinations, add new combo. So the dead load here will have a scale factor of 1.2. We'll add that to the table. And then for live load, that'll have a scale factor of 1.6. And we'll add that to the table. So we've got dead times 1.2, live times 1.6. And then we can say OK. And now we have our load combination 1. So then we can say OK. All right. Any questions on that? Awesome. Okay, so last thing we need to do is actually put in our loads now that they're all the background for them is set up. We're going to have 2 point loads on the structure. So if you recall, that's another unique thing about trusses. They're only loaded at the joints and not on the members themselves. I mean, in reality, they can be, but on a perfect theoretical truss, we only want them to be loaded at the joints here. Otherwise, you're going to get like bending and stuff in the members, and it's going to turn out different than the equilibrium equations will tell you. So for load D here, we're going to have a dead load and a live load that is represented using this vector here. If you remember back in vectors, you can go and decompose them into their x, y, and z components. So 2i plus 6j is going to be 2 kips in our x direction and 6 kips in the y direction. And then same thing goes for the load at point G here. We'll have 4 in the x, 3 in the y, and 5 in the z direction here. Okay, so we'll go and do those. So let me go, and those will both be dead loads and live loads. So let's go and click on point D here. We'll go and assign a joint load and force. So let's start out with our dead load. So that option's good there. Then in the x direction here, we'll put 2. And in the y direction, we'll put 6. And then we'll say, okay. Now let's select that again. We'll go to assign joint loads forces. And then we're gonna, because we already have the numbers in here, let's go and switch from dead load to live load and say, okay. So now we have both of our dead load and our live load at that joint right there. So like if we go and right click on the joint there and look at our loads, we see that we have both X and Y direction loads for dead load and live load. Okay, now we'll do the same thing for node G right here. So we'll go to assign joint loads forces. We're going to put in 4, 3, and 5 for Z. This one's in live load here, so we'll say okay to that. And then we'll do the same thing again for dead load. So 4, 3, 5. And then we'll say okay. So we have our loads in there. Okay, any questions on this? Okay, so that's our geometry, that's our loads. We're now ready to run the analysis, so we can hit the button to run it. Let's not run the modal case, say run now. It'll ask us to save it, so we'll do that. Save that again, and it will go and run real quick. And then we'll get the dead load deformed shape there.
Did you not run the model? Or do you also consider, do you leave it on?
I usually turn the modal off. So the modal analysis figures out the modes of vibration of your structure. So that's useful in dynamics. We're sticking with statics for now because it's easier. If you want to get into dynamics, we've got lots of fun classes on those. Okay, so everyone's model run, get something that looks, not too bent out of shape. Something like this, at least. Okay. So we've got a couple deliverables. So first off is reactions for load combination 1. So we'll go to display, show forces, stresses, joints. And here's where we get our reactions. So we'll switch it from dead to load combination 1. Press OK. And we've got all of our reactions here. Now you'll notice these are kind of pointing downwards and outwards from the truss. That makes sense. And these ones are kind of pointing that way and upwards. So these two are kind of getting pushed down into the ground, and this one's getting pulled up from the ground, which makes sense based off of the kind of magnitudes and the directions those loads were pointing in. So when we're designing this eventually, we need to be careful that we go and consider these reactions here. So as a lot of the time with foundations, we're thinking, oh gosh, the building's going to be so heavy. There's no way it's going to be having a force going up. But depending on the lateral loads we get sometimes, it can start pulling the building up at the foundation. So we do need to be careful about that. Okay, so that's our reactions there. So that's pretty easy for the report there. Next thing is our axial forces for load combination 1. So we'll go to our axial forces there. So we'll go to display, show forces, stresses, frames, cables, tendons. We'll switch it to load combination 1. We'll keep it on axial force here, and then we'll click on show values. Then we'll press OK. And now we have the axial diagrams for all of the members in the truss here. And if you notice, all the blue ones here are in tension, the red ones are in compression, and we've got quite a few zero force members in the truss here as well. Because these outer kind of edge bars here are concurrent, so the angle doesn't change at this middle node here. These middle bars here wind up being zero force members, and so do the ones down at the base here, because we have because we have 3D pins at each of those reactions there. Okay, makes sense with all that? Okay, and then we want to find the deformed shape for load combination 1. So we can go to display and click on deformed shape here, or click on the same button up here. We'll do the same thing. We'll go and click on load combination 1. I'll turn on the wire shadow, and then we can say OK. And we get the deformed shape due to load combination 1. And then finally, we want the horizontal and vertical displacements of joints G and D for load combination 1. So those are going to be the two joints you added loads to. So that'll be this one here for D, I believe, and this one here for G. Now it wants both the vertical and the horizontal displacements. So of our numbers here, which one's the vertical displacement? Yep, it's going to be U3. So 1, 2, and 3 correspond to X, Y, and Z respectively here. So U1 and U2 are going to be our horizontal, because we're working in 3D. We have two horizontal dimensions. And U3 is going to be our vertical displacement. And then we'll look at the same numbers for this node up here. So we want U1, U2, U3 for that node, then U1, U2, U3 for that node. And when you're writing your report, you can just go and like write these numbers down in a table in your report. You don't need to go and like take screenshots and stuff like that. Yeah, and because it's a 3D truss, if you look at any of our nodes here, there should not be any rotation values. So R1, R2, and R3 should always be 0 for any of the nodes in our truss here. Okay, and that's all of our deliverables. So, pretty simple lab. Any questions? All right, so now y'all are masters at modeling 3D trusses. So I'll put up the assignment, and that's a similar one to this. On the assignment, there's a directional force on there. I didn't break it out into components, so it's easy enough. It's a 3, 4, 5. You can go and break it out into components yourself. You should be able to do that. But yeah, if you have any questions, let me know. All right, so that's all for lab this week. Thanks for coming. For sure.